I am a bit of outlier in this session, but anyway. So it's good to be back here to Santa Cruz. And what I want to present is a new model that we are developing about the galaxy supermassive black hole halo connection. So this is work in progress, and I will really appreciate your feedback about this model. So please ask questions. Well, this is the outline of the talk. Before describing the model that I would like to present, first I will describe two works that we did that actually were necessary in order to constrain the parameter space of our model. So I will start to describing how we compute a new galaxy stellar mass function at redshift 0.1, which the main point here is that we constrain it for very small galaxies to very high galaxies that are the centers of the clusters, from dwarf galaxies to massive galaxies, and also to show that how the star-forming main sequence is consistent with the evolution of the far ultraviolet and far infrared luminosity functions and the galaxy stellar mass function of the galaxies. Okay, so I will start first with the galaxy stellar mass function of local galaxies. So why we thought that it was a good idea to recalculate the galaxy stellar mass function? Normally, one uses the SDSS, which is a wide and shallow survey, to constrain the galaxy stellar mass function. The main problem is that we can only constrain the galaxy stellar mass function for above 10 to the 9 solar masses. And most of the time, we don't, if we want to use small and deep surveys that constrain small scale galaxies, we combine these two calculations in order to get a continuous galaxy stellar mass function. However, the problem to do that is that people that usually constrain here use different methods to derive stellar masses, and the way that they compute the errors, which will be different to the way that people that use small and deep surveys will constrain stellar masses, and also in the way that they compute errors. So what we thought it was that why don't we use, or why don't we try to set an homogeneous set of a galaxy sample where we can compute in a consistent way from small scales to large scales. I won't enter into too much details about that. I will just show the results. If you want to discuss more about this, please ask me in the break session, or you can send me an email. So we combined two samples, the low SDSS, which is below 0.005, and the main SDSS, which is 0.005 up to redshift 0.2. So for the small scales, the main challenge was that we need to develop an empirical model for completing the fraction of missing low surface brightness galaxies. So in our paper, we describe more about that. You can check the paper, or you can ask me. And the main result is that we develop a very consistent galaxy stellar mass function over from 10 to the 7 to slightly above 10 to the 12. So what you see here is the points are our measurements. The solid line is our best fit. We compare to a double Schechter function fit, and we notice that a double Schechter fit to the galaxy stellar mass function is not enough for this new galaxy stellar mass function. It was actually needed a Schechter plus a power law in order to constrain the massive end of the galaxy stellar mass function. Okay, so that was my quick introduction to that paper. Now, what I'm want to describe is how we combine the luminosity functions between the far UV plus infrared luminosity functions. I don't know why there is a B here, but it's supposed to be an L. So what we did in a very simple terms is that we assumed that there is a correlation between the star formation rate, a mean relation between the star formation rate and the far ultraviolet as a function of the stellar mass. We assume some parametric function, which is basically a double power law. We also assumed the same thing for the star formation rate and the infrared. And then what we assume is that there was some dispersion around these relations, okay? For the far infrared, we assume also that starbursts can be dusty. So we added another component for dusty star-forming galaxies. So in resume, our model assumes that there is a Gaussian dispersion around these relations and a double Gaussian around the infrared relation. So the idea was what if we use these relations, we convert it into luminosities by using the Kennywood relations, and then we convolve with the evolution of the galaxy stellar mass function for star-forming galaxies. As a result of this algorithm, we can derive then the luminosity function and the far ultraviolet and the infrared light. So if we play this game, then we can fit the parameters that we can assume for these two relations. And then by using the observations of the galaxy stellar mass function of star-forming galaxies and the luminosity function of ultraviolet and infrared galaxies, we can then derive what is the relation between the star formation rate and the stellar mass, not only divided into ultraviolet and infrared, but also for the total galaxies. So here are our fits. This is our fits of the far ultraviolet luminosity function for redshift 0 to redshift 10, to redshift 9, sorry. So you see here that there is a bend here. The bend is not that the number of far ultraviolet, we are predicting that the number of ultraviolet galaxies decreases, but it's just the limit in the stellar mass that we are integrating in order to obtain the far ultraviolet luminosity functions. These are our fits to the far infrared luminosity functions. This is the compilation that we use. And this is the main result. So here are our main sequence, our star-forming main sequence relation based on the far ultraviolet and far infrared luminosity functions. Okay? So we are plotting here the specific star formation rate as a function of a stellar mass. The solid line is when we have constraints from both luminosity functions, and the dashed line is when only we have constraints from the far ultraviolet luminosity function. So we are comparing here from redshift 0 to redshift 4. And well, in general, you see that there is consistent with observations where they use individual galaxies to measure the star formation rates. And we are comparing here against the medians of those samples. So there is a consistency between our relations, what is supposed to be our median of the relation, and the relations that we observe galaxy by galaxy. Now, one of the interesting things that came out from this model is that there is a turnover around below 10 to the 9 solar masses for the star-forming main sequence galaxies. So whether this is real or not, we need more data here. And at higher redshifts, it will be also interesting to see what is the James Webb predicting. But basically, at all redshifts, we see that there is this turnover around 10 to the 9, below 10 to the 9. At least for redshift 0, we can compare to local samples. So here we use the Kingfish and a sample of dwarf galaxies from Manga. So the Kingfish is predicting that around these masses, the specific star formation rate stellar mass relation flattens. And for the Manga sample, also shows that there is some indication that it flattens. And the dwarf sample from Magot 2017 also shows that it is likely to be flattened. So it is not, so perhaps there are some indications that actually the star forming main sequence is not a power law, okay? But it should flatten at some time. Now, we give some argument that if we assume that there is a constant star formation history, then this flatten will imply that the assembly history of the dwarf galaxies should be around 10 gigayears for the masses that we are putting here. So, and this is consistent with the paper by Weiss 2014. Now, if we extrapolate what we usually fit for the main sequence galaxies, the number that we will get for the assembly history of the dwarf galaxies will be only 2 gigayears. So basically, it will be a very fast formation time for the dwarf galaxies. Okay. So, and also as a free, we get the fraction, the dust obscure fraction in the star formation rate from redshift 0 to redshift 3 as a function of stellar mass. So the main result is that there is a very strong dependence of the dust fraction as a function of the stellar mass, but also that at the high redshifts, high mass galaxies were dustier than local galaxies. Okay. Okay, so that was my introduction to those 2 papers, and were necessary in order to constrain the best fit parameters of this model. Okay, so now in this second part, I will describe the galaxy-halo connection that we've been developing. Okay, so we have several approaches to study galaxy evolution. Our goal is to understand what is galaxy formation and evolution, and we can do it in several ways. So we can do it purely empirical, using only observations and tracking back in time galaxies by using abundance matching of the galaxy size mass function, for example. That is the galaxy population that I'm putting here. And also we can use the spectra from the galaxies, fit the spectra, and then obtain what was the star formation histories of those galaxies, which normally people call the fossil record. So we can combine the fossil record for a population of a complete sample of galaxies and then infer what is the evolution of the galaxy population. But also we have another way to do it. So we have a structure formation model, which say is the lambda CDM. And we can run hydro simulations, or we can also run semi-analytic models. But there is another complementary way in which we can combine the theory-based approach and the observational-based approach, in which we will use the structure formation model and the observations. And this is an interface which we call the galaxy-halo connection. The idea is that this model is very consistent with the observations, but also with the structure formation model. So it is a very useful model in order to put galaxy formation in terms into a model of a structure formation. Okay, so this is a whole industry. Several people have worked on this. And the main point is that by showing this is that when you look at the stellar to halo mass ratio as a function of the halo mass, most of the techniques that people have developed in order to constrain this relation is very consistent between each other within the systematics, okay? Which is actually very interesting. Okay, so this is motivating the new model that we are calling Empire, which comes from just the semi-empirical modeling. That was the first thing that I could come out with by just combining these words. And this is, and this model will combine galaxies, supermassive black holes, and halos. Well, what did we use? We used two simulations. We used the multi-dark Planck simulation and the Bolshoi Planck simulation. So basically, the idea was to fit the merger trees or the assembly history of the dark matter halos with galaxies and some recipes in how to project observables into the properties of the dark matter halos. In a very simple way, the model works in this way. So in the y-axis, here we are plotting the maximum circular velocity over the whole history of the dark matter halo. And here is the maximum mass of the dark matter halo over its history. Color-coded is the redshift formation of the dark matter halos. And what is here, what we use for here is the half mass of the dark matter halo. So redder means that halos assemble earlier. More bluer means that halos assemble later. Sorry. So here we have older halos, and here we have young halos. And we see that this is persistent over the full mass range of the dark matter halos. Well, this is actually not new. There is this paper by Risa Wechsler where they found that older halos, meaning more concentrated halos, will imply that we'll have a larger B peak, okay? So what we are also showing here is that if we compute the median relation here and we divide into two populations, the population above the median and below the median, and we compute the two-point correlation function for those populations in halo mass bins, so the ones that are older tend to be more clustered than younger halos. So and we see this at redshift 0, and we see the same thing at redshift 1, what is shown here. So what is happening is that halos for a fixed halo mass, older halos are more concentrated and more clustered, and halos with a lower V peak will be younger and less concentrated and less clustered. Okay. So in our idea, we wanted to correlate this with the properties of our galaxies. So what we did is to define a threshold in which above the galaxies, by crossing this threshold, will be more likely to be quiescent, and below will be more likely to be star-forming galaxies. So then if we can color code the galaxies by being star-forming or quiescent galaxies, above will be a cloud of quiescent galaxies, and below you will have a cloud of quiescent galaxies. We do this redshift by redshift. So then at every redshift, we are asking what is the distance of our galaxy in this plane to this threshold that we are putting here. Okay? So in this model, halos larger than 10 to the 12 solar masses will be more likely to host central quiescent galaxies, and the opposite for halos below 10 to the 12. Now, we also introduce an extra environmental parameter in order to check whether the galaxy, if the galaxy was satellite, we introduce this parameter in order to quench that galaxy. So also, I would like to emphasize that for this model, most of the time there are quiescent galaxies. You will have quiescent galaxies. So this model produces basically long-term quenching. Okay, so this is the idea, to produce two types of populations where the star formation rates and the way that we are developing the model will depend into two parameters, P peak and M peak. And the goal is to produce a bimodal distribution that will reproduce the observables. Okay. We also introduce galaxy sizes, and this is very important in order to put supermassive black holes. So the basic idea is to assume that the central potential produced by the stars is given by this relation. If we assume that the central potential of the stars are proportional to the central potential of the halos, then this relation should be proportional to the B peak square. Now, B peak square is not actually measured at that distance. So what we do in order to put as an equality symbol here is that we modulate by the baryon fraction at R star. So in practice, because we don't have the radial profile of our galaxies, what we do in practice is to use the stellar to halo mass ratio times some function that we will fit in our model. So essentially, our model will be given by this equation, where this function that we are introducing here is basically the ratio of the Hall mass to half-life radius. Now, we notice that this equation actually is very consistent with the Yang 2019 model, where Fanju described on Monday, and that it is consistent in the sense that they assume this form of the galaxy sizes, but here as a function of the concentration, and here the parameter was 0.7, but here we are assuming that it is 1, basically. We are also putting the supermassive black hole sizes, and this is the important point of why we need the radius in our galaxies. So we started by assuming that there is some radius of influence from the supermassive black hole given by this equation. Then, if we compute what is the velocity dispersion of the stars given by this equation, which is the dynamical mass at the half mass radius divided by the half mass radius, and then we combine these two equations, we will get this equation, where the main point here is that we can then write the black hole mass as a function of this ratio, the stellar to half mass radius. Okay. Now, it is important to note that we assume that this parameter is independent of redshift, but we fit it the data. The next point was to assign the supermassive black holes in the model. And the main point of this assignment was that all galaxies that were star forming will host basically AGNs and quasars. Okay? For quiescent galaxies, we don't know which types of AGNs are hosting. We just assume that there is some type of AGN hosting these quiescent galaxies. But we can actually fit the data by using this relation that we have only at redshift 0. Okay? In the case of quasars, we have the radiative parameter as a free parameter that we also fit to the data. Okay, so basically this is the main point, that we have developed a model in which we have a multivariate distribution for the galaxy properties that will depend in two properties of the dark matter halos, in their B peak and M peak for every redshift. We will use the observables in order to constrain the best fit parameters of this model as a function of redshift. Okay. So I'm not going to spend time showing you the best fit parameters of the model. You can ask me later, or you can check them when I put it on the website of the conference. But here are all the fits that we are using, and we can come back later. So just in order to finish my talk, just the main results of the relation of the talk. So here we are plotting the stellar to halo mass relation. We are comparing to the universe machine by Peter Peruzzi. So we are seeing a very good consistency between our models. Perhaps our model is predicting that galaxies were more massive for a given halo mass at high redshifts. We also do clustering. We predict the clustering when we divide into star-forming and quiescent galaxies for redshift 0. This is also for redshift 0, but also to redshift 0.5 and redshift 1. So we see that there is a good consistency. We also slice the star-forming main sequence into the samples that we are showing here. And the solid circles are the observations. And the predictions from the model are the solid lines, which you see that there is a good consistency. We did this comparison in different ways by slicing in different manners, the star-forming main sequence versus the stellar mass. And again, we see that there is a good consistency between the clustering and our model. Another way to show it. And the results of the clustering were consistent between each other. So now what I'm showing here is the black hole mass versus halo mass relation. So we also have the constraints from redshift 0 to redshift 10. We notice here that we have some predictions of very high mass supermassive black holes at high redshifts as well. And what is very interesting is that if we compute what are the energies, the feedback energies from supernovae and from the black hole accretion, if we focus in this panel where we are showing the ratio of these two energies, red means that the binding energy is larger than the energy of supernovae or the black hole. And blue means that the energy from the supernovae or the black hole is larger than the binding energy. So this panel in the middle is showing how is the binding energy history for the supernovae, for the supernovae. And we see that for halos below around 100 kilometers per second, what we see, something that I forgot to say is that the white color means that these two are equal. So basically around 100 kilometers per second, we see that both are equal in the case of supernovae. And in the case of the black hole feedback, we see that this depends very strong with mass, but around the line where we have the equality between the quiescent fraction and the star-forming fraction of galaxies. Well, just just to end my presentation, we have also a mock catalog that we designed for the Toltec collaboration, which is a 100-degree simulation in the submillimeter. So basically, we create a light cone with this area where the star formation histories were used in order to produce the history of the dust of the galaxies. We compute what is the counts in different bands in the submillimeter region. The solid lines is the model. The circles are the observations. We see also that this is a very good prediction of the model. And basically, what is more important for the Toltec collaboration is the counts at 1.1 millimeter. And here, the solid line, here is the cumulative counts at 1.1 as a function of the flux. So the solid line is the model, and the circles and the symbols are some different observations. Okay, so I will let you with my summary, and I will take questions if there's any.
Yeah, thanks for the nice talk. I just have a question about your parameterization. So it seems that you are parameterizing the galaxy's star formation rate history with as a function of the peak rotational velocity or the peak mass of the dark matter halos. So is it true or is it correct to say that in your model, in Empire, the star formation history has nothing to do with the recent halo mass accretion history of dark matter halos? It's just a function of your peak value in the history.
Well, in some sense, there is a connection because actually in this plane, we need to decide whether it is a star forming or quiescent galaxies. So if it is growing in M peak and you cross the line, well, you will be a quiescent galaxies and you will have a different star formation rate, more consistent with quiescent galaxies.
Okay, but this fraction doesn't, I mean, whether you decide which galaxies are star forming versus quiescent, it doesn't have anything to do with how much the halo has accreted.
Right, but
since the peak,
you can be here,
yeah,
and then accrete mass. It was your M peak here, and then you accrete mass, and you go and you cross here.
Okay. Yeah. All right. Thanks.
Very impressive work as always. Quick question. So it appears that both in the first part, when you take star formation, you have a model for the star formation rate and the stellar masses, and you go to make luminosity functions, and in this work, throughout, it seems that you're assuming that all star formation makes stars that end up in galaxies that are accounted for by the stellar mass function. And back when we did this 10 years ago, when we were playing with these kind of things, we always noticed that we ran into problems when we tried to just fit the satellite stellar mass function. We were vastly over-predicting it all the time in a self-consistent fashion. And I mean, the solution was sort of to take a lot of satellites and disrupt them and make interstellar light. And actually, the total amount of interstellar light is quite substantial. So I was wondering whether you have thought about that. And
yeah. We are taking into account what is the fraction of the stars that will be into intra-halo light, actually. So yeah, so all of that is included. Yeah,
but not in the first part, right? Where you
you
made assumption star formation rate, took the stellar mass function,
yeah,
and then
not in this part. No. But in the second part, yes.
So you have a parameterization for satellite quenching, right? That epsilon parameter, is it how is it constrained? And have you made some satellite quenching predictions? I know it's wrong Bolshoi, but you still do have some satellites, right?
Right. So in our constraints, actually, we just, in order to fit that parameter, that environmental parameter, so we use the quiescent fraction of centrals and satellite galaxies.
Okay, so I suggest that the next speaker comes and that we thank Aldo again.